Alright class, so I just figured I would start this video kind of going back and fitting that model that we ended the last video with here in R, just sort of as a reminder. So even though my data set is already loaded, I'm going to kind of show you how to again load that data set that you would need just from, basically again it's an Excel file, but it's saved as a .csv is how I have things saved here. So then I'm just browsing to where I've saved my file. And again, down here you can change the name of that data set if you would like. So I'm going to go ahead and call it place.kick. And then import it. So again, I'll kind of show you what that data set looks like. Now again, I'm going to fit the model here. So just as a reminder, so the function that I'm using in R is called GLM. Mod.fit is what I'm storing those results in. So again, this mod.fit part, I can name anything I want. My response variable was whether that kick was good, where a 0 means that it was a missed kick, and a 1 means it was a made kick. And then dist is my explanatory variable. Those are the exact same names as what's inside my data set here. So there's that good 1 and that distance. The name of my data set is called place.kick. In my family, I'm using the binomial because that's the distribution that I'm following here. Our link function is called the Logit Link. Again, we will talk about other ones in another video. This is just saying if I have any missing data to exclude those observations. And again, the rest of this is to kind of know at what point I'm going to stop trying to estimate my parameters. And then we're going to run that. So now I'm just going to run that line of code. And again, since I've stored it in something, that's why I'm not getting necessarily a lot of output. That names.fit again just showed me what things are inside of that I could ask for. The first thing I asked for was the coefficients because that gives me my alpha hat and my beta hat for my model. Then the summary function is going to give me more useful information for hypothesis tests and the like. And so we also got our alpha hat and our beta hat there. So using that is how we got our model from last time. That looked like that. So here's our model using that alpha hat and that beta hat. Again, remember that our beta hat here was actually negative, which made sense to us, because that would mean that you are less likely to make a longer kick than a shorter kick. Then we also found our estimated probabilities using an X of 20 and then an X of 50. So last time we plugged those values in together. When X was 20, our estimated probability of success, so I'm going to make sure I actually put the 20 in here, turned out to be about 97%, a little bit more than that. And then when X was 50, our estimated probability of success was just a tad bit more than a 50% chance, which is still actually not too bad of a chance for a kick. We did also briefly talk about how the Z is going to tell us if the corresponding parameter is 0 or not. Basically trying to tell us if our value is useful or not. So looking at our slope-ish coefficient, looking at my Z value and my P value that I'd see there, I would see that distance is going to be a useful predictor for the probability of a successful place kick. So very quick rundown of what we did last time. Now that I have my model, What I might be interested in doing is trying to get a plot of the actual fitted value, so the plot of my pi hat. The plot you see here is a very, very rough one. It's not a very pretty plot. What we're seeing here is my estimated probability is on my y-axis. That's my estimated probability of success. And down here is that distance, or my x. So how I got this plot was I just used the data in the actual data set. So I used for my x the actual distances. And then for my y values here, I'm trying to get the pi hat values. So let's kind of notice what I'm doing different. This says place.kick. That's going to pull off from my place.kick data set the actual data. This one for my y, I'm pulling off my mod.fit. So this is going to be now not looking at the actual data. It's going to pull off from this new data set I've created of this mod.fit. It's pulling off those fitted values. Which, going back here to R, scrolling up here a little bit, that is one of the things inside of my mod.fit. So it's going to give me the fitted values for every single one. Now, just to actually show you what's in that first, let me actually show you what's just inside this mod.fit fitted values by just running that. It's going to be big as a warning here. So what you have here is the fitted value for every distance in my data set. What you'll notice that a lot of the values are exactly the same, because if I attempted 25 20-yard place kicks, it's going to have 25 of the same value because it's going to be the same estimated probability of success. Just as what we had up here. So every time I plug in 20, we're going to get this 0.97045, and you'll see that number show up a lot. So a lot of the values in here are going to be the same, simply because we have some of the exact same x values showing up again and again. Then what we're doing is putting some labels. So on the x label, I'm putting the word yards, and the y label, just the estimated probability, and that will get me that corresponding plot. So now let's actually just create the whole plot. So here's our estimated probability. Again, you can always change the size of this if you would like. And kind of play with that to get a different looking plot from there as well. So here's my estimated probability. Notice how there's some gaps here. Now the reason why those gaps happened is because this is only getting me estimated probabilities for any values I had in my data set. So if I didn't attempt to kick at, say, 58 yards, it's not going to give me a fitted value for that 58 yards. So this is kind of a very rough plot using just the data itself. However, one thing I would also like to do is actually have not just a plot of my fitted values. I would like to see how that looks over my actual data. Well, what becomes a little bit harder here is how would I actually get a plot of the data? Why is the data here a little bit trickier to look at? Well, go back to our data set. Our response variable is just a whole bunch of zeros and ones. So if I imagined I would just have some plots at either 1 or 0 this whole way across. And that's not really going to give me a very useful idea if this plot is really fitting my data well, when my data is just a whole bunch of zeros and ones. So what we could do instead is we could find the sample proportion that are successful at any given distance. So what I mean by that. So suppose we attempted 10 20-yard kicks. of those, we made 9. So instead of having a plot at 20 yards where I have 9 ones plotted and 1 0 plotted, I'm going to instead plot 9 out of 10 or 90% as my data value at 20 yards. Because that's going to give me a better idea of, well, based upon my sample, what proportion of the sample did I make at that distance? Will give me a much better idea to see how well my model is fitting the data if I actually have proportions instead. So now we're going to talk through the code. Again, keep in mind here in the handout, this is the RAN code, so you have output along with the code. So we're going to label some things here, of course, as we go. Now, the first thing I'm actually going to do here is create a table. So in this table, I'm going to do basically one row is going to be for each individual distance. And then for my columns, I'm going to have it be for the good one. So for each distance, it's going to give me how many zeros I have and then how many ones I have. So then what I just did here next is actually spit out the first 5 rows so that we didn't have to look at the entire data set here. So the smallest distance we had was 18 yards. We had a total of 3 attempts. 1 of those was unsuccessful. 2 of those were successful. At 19 yards, we had 0 kicks that were unsuccessful and 8 kicks that were successful. At 20 yards, we had 13 kicks that were unsuccessful and 776 that were successful. Now, as an aside, why the 20 was so large is at the time that this data was collected, 20 yards was the standard distance for a point after attempt. So that's why there's so many of those, because that's considered a place kick as well. At 21 yards, we had 1 unsuccessful kick and 19 successful kicks. So what I can also see here, so for example, let's just focus on this 21 distance with 1 miss and 19 made. If I want to calculate then the proportion of ones, there were 19 kicks made. Out of the 20, the 19 plus 1 total kicks attempted at that distance, which is going to give me 95% of our sample kicks were made at 21 yards. Next thing I'm going to do is put the data in a little bit nicer looking format. It's going to have the same numbers idea of going on up here. Just going to be summarized a little bit different and include some other values here as well. Again, reminder, anything that has this pound sign in front of it is just a comment in R. So the first thing it says here is I need to get a special package that's going to have this GSummary function in it. So the first thing I'm going to do is run that library function. I'm going to go back here and run those other 2 lines that we already just looked at. Okay, notice that's in green here in my code because those are just comments. So I'm going to go ahead and run this library. Depending upon your computer, that may take longer for some of you than others. But if I do not run that library, when I try to use this GSummary function later, it will not work. So you need to make sure you run that library first. All right, again, let's talk through some of this code here first. Right, so remember, anything here to the left of an arrow is just sort of what I'm naming something. So I'm naming this place.k2, so kind of like place.kick2, just have a different name for it. I'm going to create a new data set, so I'm going to create a data frame. I'm going to call good, my response variable. It's just going to be the same thing as it was from the original data set. So go into the original data set of place.kick, pull off that good one variable. Also, I'm going to put the distance. I'm just going to call it dist. It's going to come off that place.kick $distance. So if I were to run that line of code, we're just going to get a new data set, but it's only going to have those 2 variables in it of whether it was a successful kick or not and its corresponding distance. Right, in my next line of code, I'm going to be getting the total number of successful place kicks. I'm going to call this place.sum. So gSummary is the function I'm going to use. The object I'm going to use is this data set I just created. Right, so we're going to go to this data set. Fun just stands for function that we're going to use. And for this function, I'm going to use a sum function. So I'm just going to add up some values. We're going to create groups so that it knows kind of what to sum over. So it's going to sum over based upon distance. And this might seem counterintuitive. So it's going to do grouping based upon the distance. So it's going to put all the 18-yard kicks together, all of the 19-yard kicks together, all of the 20-yard kicks together, and so on. So it's going to create basically one row for each distance, which is what I want, and then it's going to sum that other variable for me that's in my data set. So let's run just that line so you can see what's in that. So now in my new data set, my place.sum, it has how many kicks were successful, as well as the distance that kick was attempted at. All right, so remember, so what good is going to be is the number of successful place kicks. So it's the same thing that we had here, this 2, 8, 7, 76, 19. It's doing just that column for me. So right now I have the total number of successful kicks. My next line of code is going to help me get how many attempts there were at each distance. So for this one, I'm just calling it place.length. The length is going to tell me the number inside of it. But you'll also notice the only thing different in my next line of code is the function I'm using is now the length function. So the length, what that's going to give me is my number of attempts. And then because I'm using the distance here for each distance. So what this is going to do for me is it's going to tell me, well, there was 3 kicks attempted at 18 yards. There was 8 kicks attempted at 19 yards. There was 789 total kicks attempted at 20 yards. So my first one was just getting off the number of successful kicks. This one's going to get off my total number of attempts at that distance, like our 20 that we have here. All right, so let's run that line. And then you can always look at it. So again, by distance, total number of attempts that we're looking at there. Now my next line of code is actually going to be calculating those sample proportions like we did up here. So I want to know that there was 95% of my kicks attempted at 21 yards in my sample that were made. So in order to get this, I'm just going to call this my prop. That's just standing for proportion, is what I mean by that. Again, that's just what I'm naming it. So what I'm going to do is I'm going to take my place.sum. Remember, this was my total number of successful kicks. And we're going to divide that by our total number of attempts that we have. Okay, so let's run that line. So now I can see in my proportion that it's just a whole bunch of numbers. So 0.667 is just doing, there was 2 kicks made out of the 3. All right, finally, I'm going to put this all together into one data set. I'm going to call this new data set place.pattern. I'm going to create a new data set. My Y is going to be my place.sum $good. So place.sum $good. Our N Then it's going to be our place.length $good. So this gives me my number of successful place kicks. This will give me my total number of attempts at that distance. My proportion, I'm just going to name proportion again as well as prop. And then for my distance, that's going to be my place.sum $distance. So remember, going back to those data sets if we need to. So here's like my place.sum. We're going to pull off that distance column there for us. There as well. So I'm putting that all into one data set together, and then it's going to pull off the first 5 rows for us to look at, which you already see there. But let's go ahead and run that here as well. So then here's our first 5 rows for those first 5 distances. Let's go back here where I can write a little bit more easily. So what I'll see here is at 18 yards, there were 2 successful place kicks out of 3, which is 0.666667. So right how I'm getting that 0.6667 is it's just that 2 out of that 3. This 1 is coming from 8 out of 8. The 0.9835234 is coming from there are 776 successful kicks out of that 789. So it's just calculating how many kicks were successful out of how many, giving me that proportion as well as tell me what distance that was at. Okay. Next thing we're actually going to do is use that to create our plot here. So for my plot, again, my x is going to be that distance. I'm just pulling it off from my new data set, but that's going to be the same as it was before. Y, what I'm going to plot now, is actually going to be that sample proportion. So this is going to be actually the plot of my data. Okay. Again, I'm going to label things here as I go. So my x label is just going to be distance measured in yards. My Y label will also be estimated probability. Main is just putting an overall title onto my plot, and I'm going to call it estimated probability of a successful place kick. Let's just run that plot so you can see what happens. So what you'll see with this plot is there's no model on it. This is now, right now, just a plot of my actual data. So what we saw was at 20 yards, right, we have about that 0.9-ish percent chance, sorry, 0.988. So here's that 0.6667, 1, 0.98352234, 0.95, 0.85. So it's just all of those sample proportions that I just created here that are being plotted for their given distances. Now what I would like to do is actually put my model on top of this plot. So first I'm going to do distance 18 to 66. Now first explaining what this is going to do. So what this is going to do here for me is it's going to do a distance of 18. I started there because that was my smallest distance. It's going to do 19. It's going to do 20. By default, without me specifying otherwise, is it's going to continue to go up by 1 until it hits 66. Now what I'm actually going to do is fit the model for each of those distances. So what I want to do here is I'm going back to my original model. I'm going to plug in 18 for x, 19 for x, 20 for x, and just keep doing that for all of my values from 18 to 66. But what's of course nice about R, I can do all of that in just my code instead of having to do it by hand. So the first thing I'm doing is creating what I'm calling my lin.pred. This is my linear predictor. What this part is doing here for me is it's just doing the alpha hat plus beta hat times x. alpha hat is going to come from mod.fit $coefficients 1. Let's talk through again why that would be what I want. Okay. When I spit out my mod.fit $coefficients, I had two different values. The first one was my alpha hat. The second one is my beta hat. So when I want the first one, I'm going to pull out that first element to get my alpha hat, and then the second part of it to get my beta hat. And so now what I need to do, all we've done so far is just basically what's kind of in this exponent here. So now to get pi hat, I need to take e to that value I just found over 1 plus e to that value. Or what I'm going to do here is I'm going to do e to my lin.pred over 1 plus e to my lin.pred. So that's what I'm doing in my code next. So I'm going to take e to that lin.pred over, and be careful with the parentheses, of 1 plus e to that lin.pred. So let's just run those lines here now. So get my distance, do that lin.pred, and my pi hat. So in my pi hat, this is going to be for 18 yards, 19, 20, 21, 22. So it's going to be in that order from that 18 to 66. Next, I'm actually going to put this line on my graph. X is still going to be my distance. Here it's this distance that I'm referring to, that 18 to 66. Y is going to be this new pi dot hat that I created. This LTY is just saying what kind of line type. You can always Google line types in R to find different ones, but this will tell you, in a sense, is it going to be a dashed line, a dotted line, a solid line, all of those different types of things. COL just specifies what color you want that line to be. I'm just going to make it red. Again, you can always just Google colors in R if you want to try to find some more cool colors to use for it there. Now what's important about this lines function is it's going to take whatever plot you currently have up and put that line on top of it. So you already have to have a plot created for this line function to put a line on a plot. So I'm going to run this lines function, and so it's going to just go right on top of the plot I already had. Just to save this for later, because we're going to use it to compare some other values later, I'm just going to store these pi dot hats into something I'm calling logistic.pi.hat, just so we have them for later. We'll get back to that plot. Okay. So let's first talk through this plot a little bit more. So here is our plot of now our fitted model, which is our red line, along with our data values that are our sample proportions, so it can kind of give us a better idea to see if our model seems to fit the data well. So it might not look like the data fits well. So why is that actually not necessarily true? Well, what I mean by that, so overall it seems to be going through the points, but you kind of have this point right here that it doesn't really seem to fit with. We got some sort of kind of other extreme values, and it doesn't really seem to be fitting all the values that well. Well, what we have to be careful of is that here at some distances there were not that many attempts. And so why that's actually a problem here for us, and let's actually go back and look at our place.sum one here, for example. As you'll see is at these extreme distances, right, there was no kicks made. But more specifically at those distances, there was only one attempt at each of these extremely high distances. At that one that was pretty far off, there was only 3 attempts as well. So when I'm looking at this graph, even though this doesn't seem to fit in the data well, this was only 3 total kicks there and you missed 1. Here there was only 1 kick attempted at that distance. Here there's only like 1 kick attempted at the distance. Why that's important, if you only attempted 1, it's either going to be none of them were made or all of them were made. Right? Because we have those zeros and ones, it makes it a little bit harder. So it might be nice to know how much data makes up those points, which I know I have those values here in R, but it'd be nice to be able to explain that with a picture. And through this picture, we're going to use what's called a bubble plot. What a bubble plot is going to do is it's going to take this point and you can make it proportional to another variable in your data set. So for example, I can make that proportional to how many observations are in my data set. In order to create a bubble plot, my new function I'm going to use is called symbols. This is going to allow me to create those big circles and smaller circles. What we're going to still use is we're going to still use our place.pattern $distance as our x, so we're still plotting distance. Our y is still going to be that proportion, our sample proportion of successes. What's new here is this circles function. Now, a big thing I want to explain here is the function I'm using here inside of it. All right, first let's talk through the variable. I'm using place.pattern $n. So if I go to place.pattern, n is my number of attempts. Notice that we had some small numbers, but we also had this really big number of 789. So I'm going to be doing circles that are going to be proportional to that variable. What you'll notice though that I did here is I'm doing the square root of that value. This is not necessarily important. What I mean by it's not important is you're not necessarily going to have to always use square root. What we're going to have to do, which again I know some of us don't like, is I'm going to have to kind of play to see what looks best. And I'll show you what happens if, for example, I don't do that square root here as we do it. Again, I'm just going to put my labels on there. So my x label is distance, my y label is estimated probability. Here I'm just putting some limits on where I want my x to go from here, from 10 to 65. My y I'm letting go from 0 to 1.5. It might seem weird that I'm letting it go to 1.5 when our highest probability is 1, but you'll see why. And then going to put our main title on there as well. Then this panel.first, just going to put some grid lines, using some dotted lines here for that. So let me first get rid of that so we can rerun this function. Okay. So now just running that symbols function. Here is our new plot. So now what you can see is kind of why I had this go to 1.5, so you could actually see this really, really big circle. Because this is that 20 yards where we had the 776 attempts at it. I'm also going to put that same line on it that I put on it before, so we can kind of see how well the data fits our model. Now, just as a difference, let me show you what happens if I don't use the square root function for my symbol here. Let's suppose all I'm going to do is take out the square root piece of that and rerun the exact same code. So now you're going to see that that really big circle stayed there, but now all you kind of have are these tiny, tiny little specks. So it really makes it a little bit harder to see even these little data points that are down here. So I don't want to lose those pieces of information, which you're having that big circle overwhelming since it's 776 compared to like 1. It's not allowing me really to see the data. So when I say you're going to play with this, is I kind of have to play with to find a function that seems to work best for my data to visualize what's going on. Because I still want you to see other sized circles where there's these like only one observation versus a few more observations as well. So now let's kind of make some comments looking at our picture here as well. All right, so here is our picture. Again, unfortunately, it's not as pretty here, but hopefully what we can see is what we want is we want this red line to be very, very close to the bigger circles because there's more data there. And I'm less concerned if it's further away from the smaller circles. So I expect this line to hopefully follow more of the data and to possibly only be off very far where I don't have a lot of data representing it. So again, following kind of the big circles as best I can. And then when I'm at least not maybe fitting as well as I think I should, I can at least see, well, those are pretty small circles. So maybe I'm not as concerned about it. All right, hopefully at this point you would feel good in creating the model in R, using it to plug in values of X, like find the estimated probabilities. I want you to also feel comfortable with using R to create this bubble plot. So things that helped us get there. We needed to create a new data set. Let me kind of pull up the one overall, this place dot pattern, which had my number of successes, my number of attempts at that given distance, and then I created the sample proportion. So I want you to go back, look through that code of all of the stuff that we created, see if there are questions on where things came from, paying close attention to what I name things and how that's different than sometimes the functions you have to use. When you have this kind of this $sign, again, remember that's just kind of pulling off a variable inside a data set that you're working with. So if things aren't working, for example, pull up place.kick, and you can make sure that you're using a name that's inside of it. So for example, again, place.kick $good1. I can see I do actually have something named good1 in my data set there as well. Okay, if you have questions, please go ahead and drop me an email, discussion board, or something like that before you move on to the next video.